I probably should have included this in the last segment, but the idea of refrigeration systems can stretch out to being very complex key components in the operations of large buildings. So here we have really now, we've looked at kind of small refrigeration systems that heat and cool our houses, but in larger applications, they're called chiller systems. And they're working on the same idea of a condenser and an evaporator to transfer heat, except that the evaporator and condenser are now next to each other. And the way we're transferring the heat is by moving it through fluids, liquids. So we chill water to cool buildings in the interior, and we reject that water heat in cooling towers where we actually have towers that evaporate off moisture. This is a video for that. I invite you to click through the slides and watch that. It really explains this whole process. But at the heart of it is still that idea of the refrigeration cycle and that idea of efficiency of performance. So you put in 1 BTU of electrical energy, and you might get out 3 BTUs of heat transfer. But it is how many commercial buildings deal with the heating and cooling requirements that they have. So let's just quickly move on through to heat. In this case, we are now discounting the idea of moving heat to refrigeration systems and looking at a much more traditional way that we heat our buildings, and that's to directly burn fossil fuels, natural gas. We can use electricity and resistance heating, but predominantly today we heat our buildings with natural gas. It is inexpensive and it is readily available. It's inexpensive for some ways negative environmental reasons because we use fracking, which has an environmental impact to it, but it has driven down the cost of fossil fuels. So in many cases, conventional fuel heating systems can be the most efficient, cost-effective way for a building to utilize energy. Um, but this is a good graphic here, just to kind of describe this idea of um, for architectural reasons, this idea of either heating water and moving it through baseboard systems into radiators or supplying air to rooms that is heated. And the difference here is an air duct. This is moving 1 kilowatt of energy. An air duct needs to be much larger than a water pipe to move the same amount of energy through the building. And that's important for architects because air ducts will take up much more space. That means the space between the ceiling plane will need to be larger. And water pipes can be very small, so we can move them. We can take up less of our interior real estate, so to speak. So that may be advantageous. Some of that discussion is changing today because it's becoming more and more important that we bring fresh air into our buildings for health reasons. So these are always trade-offs, but this idea of air ducts requiring a much larger amount of area to distribute the same amount of energy to warm and cool the space is an important consideration. So a little bit about what's inside of heating systems, natural gas heating systems, and that. There's a heat exchanger. I just wanted to expose you to this. This is a device you would typically see in a basement. These are the gases, the natural gas. This is a fresh air intake. Goes in. It passes through a heat exchanger. Um, um, Down at the bottom, it meets the fuel and is in combustion, and it snakes its way up through the heat exchanger until it's exhausted through the smaller pipe. And in an efficient furnaces, it's called a condensing heating system, which means that the heat that comes off of it is had so much heat extracted for it that it's already starting to what's called condense, which means moisture is starting to come out of the flue gases, and it's starting to get very close to room temperature. So in many cases with these condensing heaters, they have collections for moisture that comes out from the natural gas that's getting burnt. Now, the important thing about that is the combustion air is inside of one chamber, and the fresh air that goes by it is in another one. So they're separated from each other. There's no mixing of the combustion air, the heated air, or the heated gases of natural gas in the air that goes by it. That's one typical form of heating systems. An architecturally important or interesting one is this idea of radiant floor heating, where we introduce the heat at either on the ceiling plane or radiant heating or in the floor plane. In this case, these are electrical cables underneath the ceramic floor, and they're warming the surface of the floor. And that has a huge advantage in creating both thermal comfort and energy efficiency. So here we have this idea, we've just discussed this idea of a furnace that blows air around. So what happens is hot air typically likes to rise. So we get this temperature gradient from the head down to the feet. Our feet feel cold, our head feels hot. We're not comfortable, necessarily as comfortable as we can be in the environment. With the idea of the radiant floor heating, we introduce the heat at the floor. There's less room air circulation because we're not forcing the air into the room, so then there's a natural gradient that occurs to it. And the temperature gradient across our body is much more comfortable. We're much happier breathing cooler air and feeling warmer down at our feet level. So this all allows us to do another important thing, and that is to reduce the overall temperature in the environment. Typically with radiant systems, we can set our thermostat down about 5 degrees, and the occupant experiences about the same level of comfort. And I'm just waxing some general terms there. That idea of 5 degrees, it could be different, but that's the general concept behind the environmental, or shall we say, energy efficiency concepts of radiant floor heating. And then one last couple of clips to finish this off. It's really kind of like the visual impact of our heating and ventilation systems in our buildings. So here's a restaurant on Elmwood Avenue in the city of Buffalo. Really beautifully designed, or interestingly designed facade, if not beautiful. But here's the back side of the building. And this is really one of the concerns that you will have as architects with the placement of components. So here we have an air handler up on the roof, condensers for air conditioning systems, air exchange systems, and all of these create a huge amount of visual clutter that you need to deal with as far as masking them or putting them and placing them in places on the building that are less visible to the general public. And the same thing goes with this idea of interior ductwork. And we're going to do this in our lab. So in this case, we have spiral ductwork, which is really used as a decorative feature. This is left exposed. It's considered to be to make it look like it's an industrial or high-tech building. But there are applications where you'd want to enclose it. So here's the same construction site, but a different area. And now the ductwork you can see is up here on the top. It's been enclosed with some metal framework, and this will receive drywall over it so that it'll be completely disguised. So this is the idea of the difference between a living area and a communal area where we might want to have a more industrial aesthetic. But that idea of the choice of ductwork, this will be part of our lab, and the aesthetics that go along with it is an important consideration. And then there's an article here on this kind of hidden cost of open ceilings. Open ceilings, we're going to do that in our project, and this is kind of a counterpoint to that idea about what goes into the idea of not hiding all of the componentry that goes into our office ceilings. So this is hyperlinked, and I would invite you to open that up in the slideshow. One of the nice advantages we're going to have in our lab is the ability to place our HVAC unit on the roof by using a BIM component that already has all the parts and pieces in it, so we can actually visualize it. I want to just draw a reference to this graphic because we're going to put that on our building in our project. But I wanted to show you, here's that unit now in an actual application. So here's a unitized heating cooling system, an air circulating system. And in our project, to go along with this lecture series, we're going to actually place that same very similar type of component on a roof and then look at the idea of running ductwork to it. So that concludes the series of lectures to prepare you for your lab.